everybody to today's COSI seminar. We have Robert Swartzlander, Professor of Imaging Science and the Department of Physics at Rochester Institute of Technology. Professor Swartzlander received his bachelor degree in physics from Drexel University and master degree in physics and electrical engineering from Purdue University. Completed his PhD work at Johns Hopkins in the field of nonlinear optics. He's a fellow of the Optical Society of America and serves on both the Fellows Board and the Publication Boards of the OSA. And among other recognitions, he was named 2011 NASA Innovative Advanced Concept Fellow. He also received the NSF Young Science Investigator Award. So welcome to you.
Thanks, Ariel. Thanks. Thanks for having me here. And I want to give a little preface to what I'm going to talk about today. There'll be basically a double feature. The first show will be about solar sailing and some of the things that we're developing in that. But then I was told that you folks are very interested in imaging, so I'll talk to you about a new concept that I'm also working on for extracting information from highly sub-resolution objects. So the first show, no cartoons, sorry, but the first show, we'll be talking about how can we use sunlight to propel, not only propel through space, but to actually steer something which you call an optical wing, or in this case, a series of wings, which we call an optical flying carpet. How do we control sunlight so we can steer or sail and navigate a solar sailing spacecraft through space? And that work was based on some things that we just developed last year. This appeared in a year ago in Nature Photonics as a cover story. This shows an example, a very nice artist rendition. I think they pay their graphic artists a lot of money to come up with these beautiful systems here. But basically, something looks a little bit like an airplane wing. It may be cambered so that the top half has a different curvature than the bottom half. So you can think of it as something like a refractive airplane wing. And you might just think of it as a cylindrical lens. Cylindrical lenses, we all understand, they can focus light, but what if they're allowed to rotate because of radiation pressure? Usually you have them mounted in a system, and even if they were, even if there's some torque on them because of radiation pressure, it's going to be very small in the lab. But if these things are allowed to move in free space, or for example in a liquid, they can undergo a torque, and they can find positions of stable rotational equilibrium. They can be pushed by the light, and there can be some very interesting dynamics to these systems. So that's what we want to explore. Okay? So presumably you all understand the basic ideas of radiation pressure. It was really used, really first described by Maxwell, and it was demonstrated as a way for the first time describing why comets have this tail here. Of course, this tail is another tail because of the ions in the solar winds there. So the basic idea of radiation pressure is you probably all learned in Physics 101, is that light comes onto a surface, let's say a mirror. If all of it gets reflected, then the impulse is just twice the amount of momentum that was incident on the particle. So we say that the efficiency of this process is 200% because you end up with a factor of 2 here. And so NASA, the Japanese, and various other space agencies are very interested in launching these solar sail projects. Some of you probably remember Carl Sagan. I don't know, do any of you students still know who Carl Sagan was? Okay, so he was a big proponent of this concept. In fact, the Planetary Society was developed by him and others in order to try to promote things like solar sailing, so we can efficiently get to various parts within our solar system and outside the solar system. The Japanese launched this successfully maybe a year and a half ago, and for a mission that was on its way toward Venus, and they used radiation pressure to help change the trajectory as this craft went to Venus. I'll show another example of a craft the U.S. sent up, which is still orbiting the Earth, and it's basically just sort of tumbling in free fall. The problem with these things is that they can get propelled by the sunlight. There can be a force, but the question is, how do you steer them? What if you wanted to not just go away from the sun, but what if you wanted to move it, navigate it left or right, up or down? The conventional way of doing this is you would put little gas jets on here, and you got to move this way, and you've probably seen YouTube videos of people on skateboards doing similar kinds of things, right? So it's a limited energy supply, and it costs a lot to put something with mass up in outer space. It's extremely expensive to put anything up there that you don't need to, that has mass. So our objective is to try to find solar ways of just re-engineering the surface here so we can control the steering of this thing without the need for any additional mass, or maybe just some very light mass structures. Okay, here's an example of a NASA solar cell. It's called NanoCell D, and it's tumbling in free fall. There's really there are no ways of controlling this. They just wanted to see, first of all, could they get it to deploy? There's a funny story about this. NASA's tried several times to deploy a solar cell. This one, it basically was in this little box, and it sort of sat in there for a month or so before it just decided it's going to pop out. So there's really a lot of trouble trying to get these things to deploy properly, because these are very thin, like a mylar type of surface. It's got to be all folded up, and it has to eject and unfurl. And so there's lots of people doing research to try to understand how to do that effectively. But if they can, there's strong enough forces on here to actually make it cost effective. So our question is, well, how do we achieve something where the light's coming in one direction, but we get a force transverse to that direction? And that's called lift. So we all understand lift for an airplane wing. You have a flow of air over the wing, but the force is exerted upwards. And this is all captured by what's called the Kutta-Joukowski theorem, which basically says the lift force, let's say in the y direction, is equal to the pressure integrated over the normal every place to the surface of that wing. And so it's just an integral over the area of the wing. And if there's a pressure differential, in some cases it's because of the Bernoulli's effect over the wing, but in some cases it's just the air buttressing one side of the wing more than the other. But in either case, you end up getting a net force that lifts this thing up. And so this is also equivalent to proportional to circulation in the frame of reference of the wing. There's circulation. The air is going one direction over the top then versus the bottom. So there's a circulation, which is this gamma function here. So, and we know that there's some evidence of this circulation because the tips of these wings are unstable. They end up producing these vortices, and you can see that these things are shedding these vortices because of circulation around those wingtips. Okay. Well, so the question is there something equivalent to this Kutta-Joukowski theorem in optics? And in fact, there is. The Minkowski optical pressure, which is, you can think of it as basically h bar k, if you like. There's momentum that's exerted onto any refractive or reflecting surface, and the change in the momentum on the surface is always normal to that surface in this Minkowski interpretation of momentum. I talk about Minkowski because there's another interpretation of momentum, which is called the Abraham interpretation, which is not normal to the surface, and it's a little bit it's not quite so easy to sort of see intrinsically what's going on. So the Minkowski one is very easy because it fits very nicely into this Kutta-Joukowski theorem, where the circulation, which is proportional lift, is given by just the E cross B field of your optical beam. If you integrate over this, well, we know we can have E cross B, which is non-zero when we integrate over some closed loop in optics. So we do have something like circulation, and in fact, this could just be written. We know B is proportional to E, so you can just write it as the intensity basically times the K vector integrated over some closed loop. So it's not too hard. We can think of this as being basically just some weighted K vector, and if the weighted K vector over the top of the wing is different than the weighted K vector beneath the wing, there's going to be a differential amount of force on that object. Okay, so we just asked a very dumb question. Well, what shape should we try? Well, let's try something that looks like a wing. So we just tried something that had a semicircular cross section here, and we said, well, what if we have light in just a plane wave, okay, incident upon this? How is light going to refract and reflect off of this, and how is the momentum going to change? And that amount of force on this object is going to depend on what we call the angle of attack of the object. Because you can imagine as this thing rotates, you'll have different amounts of K distributed across the object. And so you might expect different amounts of lift force. And you might also expect a torque about the center of mass here. Okay? So we want to know, can we make this thing have a transverse, as the light's coming in this direction, can there be a force up or down, which would be the lift force? And if this thing rotates, will it find positions of stable rotational equilibrium? Will it actually torque into a position and kind of just stay there? Obviously, if you want to fly something, you don't want your airplane wing going all over the place, right? Oh, this is being videotaped. Okay, I shouldn't do that. Okay, so you know, this is one of the fundamental questions the Wright brothers asked: is how do you stabilize a wing structure? I mean, this is the huge problem they had. Is I could get maybe a few tens of yards, 100 yards of control, but eventually that instability would creep in and crash, right? We don't like that. Okay? So we have to understand the stability of this. Well, unfortunately, there's not really a closed form solution of this, so the easiest way to understand the physics of this is just to trace the rays. So for one ray coming into a system, we have some elemental amount of force, which we can just write in terms of reflection coefficients. These are just your Fresnel reflection coefficients from a dielectric interface, and we have some angle of incidence, and you can do Snell's law, and the torque on that is just going to be the moment arm crossed into whatever the force is here with respect to the center of mass. So we can just add up a whole bunch of rays and start asking ourselves what will happen. So we just sum over all the forces and all the elemental torques, and we end up getting something. Well, you can do this by hand. And as I said, you can see you don't get a closed form solution. This is not even the ugliest form of it, but we did trace a few rays to this so that we can check our ray tracing program to see if we're actually getting the right results. It's a nightmare, and one reason perhaps people haven't really done this kind of analysis because it's just so ugly. And as a physicist, I love closed form solutions, and I'm very peeved that there is not something nice that comes out of this, but this is really the only approach that I can see so far. So luckily, there's some free software called PavRay. PavRay was made for rendering photorealistic-like objects, and so at RIT is a very big school that it's one of the best photography schools in the country. I'm told we have lots of animation, 3D. We have computer graphics people who are really into image and visualization. So one of these guys toyed around with PavRay a lot. So I said, great, come work for me, and let's see if we can try to use the PavRay approach to tracing the rays. And of course, the first question is, well, does PavRay actually do the physics correctly? So we looked, and it does do the law of reflection, Snell's law. We can put in Fresnel coefficients. We can talk about polarized or unpolarized light coming in. And we can also trace either the Minkowski or the Abraham models of momentum through this system. So we know that physics seems to be about right. So now we can take, instead of one or two rays and try to trace them to the system, we can take thousands of rays, trace them to the system at any arbitrary angle of attack, and ask what are the lift forces and the torques acting on this body. So in this orientation, for example, with some refractive index of this body, the force is down here at this angle of attack, and there's a torque acting on the body to make it actually rotate. So if you see a torque vector pointing this direction, it just means the direction in which this object's rotating. The torque vector actually is going to be, well, in this case, into the page here, but it's hard to sort of really see the magnitude of something pointing in or out. So we're just drawing it like this here. So this thing's exhibiting a torque. These little green vectors are showing the direction of the Minkowski force elements every place around the surface here. So you can see there's very little light that comes out here. There's a lot of light that comes down here. And you can see the rays, a lot of the rays that are getting deviated down this way. But there's also some rays that get deviated in other directions. But from Newton's law, you can just say, well, if the light gets deviated more in one direction, there should be a force in the other direction. Okay? So in this case, the net force ends up being down this way. So you can see there's a component of lift pointing down in this direction here. In fact, I think I show this in the next slide here. We can decompose the net force into this lift component of force, and the other force in the forward direction we just call scattering force. Okay, so it's a convenient way of representing it. So I've done work at optical tweezers, and optical tweezers looks at light that's focused down very tightly, usually with a microscope objective. Here we just have uniform illumination on this object. But in either case, we can think about the forces in terms of the proportional to the power of the beam coming in, and then some factor which we call the efficiency, this Q. So this Q, as I told you earlier, could be as high as 200%, okay, because in this reflection model, for example. So we like to have a high value of Q or high values of efficiency. We can write it in terms of angular coordinates, so we'd like to have this angle of attack. Think of cosine of this capital theta being not the angle of attack, the angle of lift. It's the component of lift in the y direction. Well, I shouldn't call it y here. This is, in this case, I think x must be the angle of the light coming in, and so we like the y component here to be large. This would be basically in the upward direction, as I was showing in those slides. Anyhow, we like a large lift angle, close to 90 degrees if possible. Okay, and we like a large efficiency of torque well, we like some areas of the torque to be large, but we like to actually find out where the torque is zero at some point so that we have stable rotational equilibrium. So these are the things we're going to be analyzing, and to sum it up, we like large efficiencies of force, 10% or larger would be nice, large lift angles, perhaps exceeding 45 degrees. At the position of stable equilibrium, the torque will be zero, and not only that, the change of torque, the derivative of torque with respect to the angle of attack of this thing, okay, should be equal to zero, or should be, the slope should be less than zero in order for it to be a position of stable equilibrium. If this was greater than zero, if the torque was zero, but this was greater than zero, it would be an unstable equilibrium, which would be no good from an engineering point of view. You wouldn't want to fly a plane right at that cusp. Because it's like standing on top of a hill, you know, you're going to fall over one way or the other eventually. Okay. All right, so this shows a model of what this POV ray does. It shows an object that we're just holding fixed, but we're rotating. It's holding fixed in position, but we're rotating it as a function of the angle of attack. We're seeing the force on this changes, as well as the vector that represents the torque. Sometimes it's being torqued, would be torqued one way. Sometimes it would be torqued so that it would want to rotate the other way. So you can see it's very complex. Depends on the angle of attack. It also depends on the refractive index of this body. Okay. So we can plot out what the efficiency is here. This is the force efficiency, and the angle of the force angle, which we like to be large, as a function of the angle of attack. So if the particle was in this position here, then we would have a, let's see, so there would be a small lift efficiency, and which would be in blue. The red would show the force angle, so it would have a force angle of, you know, maybe 40, 50 degrees someplace along here. Well, this is not the point we're really so much interested in. We'd like to find angles that are large. Like we can see that for some cases, if it's at, let's say, a position here, this range here, that the force angle could be quite large, 60 degrees here, or in this orientation here, like negative 60. So we can expect to have very large transverse components of force on this object. And the magnitude of the force of these angles that you can see can be large too. So this is like maybe 25%. Okay, so we might be able to get 25% lift, total force efficiency here with a large angle, a 60-degree angle of lift. So this thing would be going up. You know, can you imagine going off in an airplane at 60 degrees? Okay, that's quite a takeoff angle. Okay, you wouldn't normally do that. Yes.
Could you explain the origin of that huge spike?
So let's see. So what's happened is it's coming around this way here. So it's going around this way here. So I suspect that what's happening is that when it gets close to maybe some kind of condition where there may be I'm not sure the polarization is here, but it could be total internal reflection or something that's happening here, that there could be a preferential focusing basically of the light off. So acting probably a lot like a lens. A lot of light just being coupled off in one direction. And so it may be that it's coming, let's say if we, well, yeah, it's difficult to actually say, okay? But I can suggest that you might wonder whether the ray optics is completely correct in all these cases. And one thing we find is these corners can sometimes give rises to little deviations, but it's just kind of a noise. I'm working with a colleague in the UK now to do some basically finite difference wave optics analysis of these systems to find out what happens in those cases. And qualitatively, they agree as we expect. Okay. So yeah, this stuff can get very messy, and to try to say, oh, it's just because of total internal reflection or one thing or another, there's no clear reason why, at least at this point. So that was the force. We also want to know about torque. So as I suggested, the torque can be negative, can be positive, okay, on either side of the axis here as a function of the angle of attack. But we're most interested in these positions where the torque goes to 0, but the slope at these points are negative, so that we would have stable rotational equilibrium. Now the question is, do you have any force at those values here? So the force, with the force angle here, you can see at this position of stable equilibrium here, you still get something like 60 degrees of the force angle here. So you can still get a substantial fraction of the total force going in the upward direction in these cases. So we want to try to ask how do we pick a material that is going to exhibit this and try to optimize the effect. So we can plot the force components. Here I show in blue the x components, which would be the forward scattering components, and the y components, the red ones, red and pink ones here, for two different cases. Now, what I showed you back here was that there's actually two positions of stable rotational equilibrium. So we want to look at the forces as a function of the refractive index for both of those stable equilibria points. And so we see that there's basically a lot going on here, but the sweet spot is the refractive index, when the refractive index of the material compared to that of the background, let's say of water, or if you had a refractive index versus air or vacuum here, that ratio should be about 1.2. Then you have a very large component of the lift force, the y component of force here. And so that's where we'd like to try to demonstrate this experimentally if we can. Okay, so this shows, let's go back here a second. This just shows, this computer simulation shows what would happen if we start off at a position that's not at rotational equilibrium. So you can see there's a large torque component on this thing. I'm just going to let this thing free fly now. If I just shine light onto this at this angle of attack, there's going to be a large lift force, so we might expect the thing to torque this direction and also undergo upward motion in this direction. And the question is, this is close to a position of rotational equilibrium. The question is, does it actually exhibit equilibrium? And it does. You can see the torque goes to 0, and the thing just ends up undergoing uniform lift in this direction. Okay. All right. So that's what we like to see in the experiment. So we set up a laser. We had a diode laser here. We sent in white light for imaging purposes, so we can actually kind of see what's going on. We block the laser light on going into our camera, so we can just see the white light here. And we just have a lens, but it's not a microscope objective. It's quite long focal length lens for this system, so that the particle sees quasi-uniform illumination. So we wanted to really distinguish this from optical tweezers. Optical tweezers would have used a microscope objective in a very tight focus here. Here we have a very relatively broad focus. The particle is on the order of 5 microns or so in size. So what the particle sees is a small portion of this beam here. We wanted to watch that on the camera, what happens. Now the particles we made were basically, we call these optical wings, were made in photoresist. So we basically just made rectangles in photoresist, and then we heated up the photoresist to let the edges flow at the melting point so that they would become curved. Then we just remove them from the substrate here and immerse them in water. So here's an example of one of these optical wings. Again, the size scale here is on the 5 micron size scale across here, and 10 or 20 microns across here. And this shows a particle just rocking. So it's sitting on the bottom of this of the glass container in water, and as we turn the laser light on, there's a torque on the object, so it just sits and rocks because of that torque. And then when we turn the light off, there's a light going on, so now it's going to rock, and then it falls kind of over the side, trying to find this position of stable equilibrium. And then when it goes back, turn the light off, it rolls back. Okay. This is an example of we've basically knocked on lab table, and we've liberated it from the surface of the glass. Now it's allowed to just move in space. So the beam is coming out of the page here. The lift force then is perpendicular to the direction of the beam, so it's in this direction here. There's also a scattering force, which is causing the particle to move out, so you can see it's defocusing here. So this was our first demonstration that we were having this transverse force acting on the object here. Okay. This was, let's see, do I have here? I have here the particle velocities. In this case, we're only on a few microns per second. But the lift angle we calculated was about 55 degrees, which was very close to what we expected theoretically. And if we put in dielectric spheres in this beam and to see if they moved at all, they exhibited none of this transverse kind of motion. So we're quite sure that this is due only to the radiation pressure forces and not to things like heating up the liquid and getting convection flow. Okay. So as I said, the goal is to remove any kind of air jets on these structures and put in some kind of optical flying carpet structure embedded into these solar sails. This is one of the next solar sails that NASA hopes to deploy. It's quite a bit larger than the NanoSail D I showed you earlier, and NASA's very interested. We got this NIAC award because NASA's very interested in trying to find ways to maneuver these things. They think it really is key to the future. But if you can again get rid of any mass of controlling jets, and if you can control this thing for a very long time, you don't run out of fuel with sunlight. You're going to have a great advantage. So the object is now not to just produce one of these optical wings, but to produce an array of those, and so that we end up getting the integrated effect as if the beam of light shines through the entire structure, then we get basically the force multiplied by n number of these structures here. So this is what we're trying to make now in our laboratory, and my graduate students trying some various techniques to make these things. So the hope is to put these things on panels on a solar sail, and if we can electro-optically basically shutter these things on or off, or find some mechanism to sort of control how much light is actually hitting these, then we can very easily control how much force we have this way and up and down. We could be able to stabilize it. This is important because these things, in order to stabilize the entire structure, many of the architectures for these solar cells are where they're rotating, so they keep a constant force to keep this solar cell deployed and keep the film tense. So you may have to be shuttering these different elements on and off in order to maintain the stability of this. Okay, so that's the first show. Okay, I hope you now understand a little bit about the theorem for lift, this Kutta-Joukowski theorem. We've demonstrated lift on these semi-cylindrical objects here. We've predicted that this rotational stability should exist, and we believe we've seen that in the laboratory. We've achieved this large lift angle. But now there's a lot to do. We really have to sort of calibrate how much force and torque are on these objects. How do we optimize the structures? Is this simple semicircular cross-section really the optimal geometry? What if we had a triangle? What if we had a trapezoid? So we're trying all kinds of different objects here. The unfortunate thing about this is that really you just have to kind of try to develop like sort of engineering principles of what works. Try to find figures of merit so we can compare one object to another and try to hone in on an optimization strategy. Okay, so here's the team on this. This is Alexandra Artuzo-Glimpse. She did the experiments, and Alan Reisen, he made fabricated the structures for us. Tim Peterson did the numerical modeling, and this guy basically said, go. Okay, so maybe I should just break for any questions about this, since we're going to move into a sort of different topic area now. Do you? Yeah.
I'm curious why you chose sort of a rendering software like FieldE-Ray to do your ray tracing and not, say, Zemax, which seems like a more natural platform for deploying ray tracing.
Because this guy came along who knew how to do great things with Pavre, and we didn't have anybody really trained in Zemax. Whether Zemax would be, so part of it was the Pavre was just doing the ray tracing, and then he wrote a separate Python-based code to do all the physics, basically calculate the forces and how to re-render it and then shove it back into Pavre. So it seemed to be pretty good. Pavre has its limitations, though. For example, if we wanted to focus light, It actually really works for illuminating objects with sort of just a wall of light. If we want to have focused light, it took a little bit of effort to try to do things like that. So we're open. The guys in computer science say that, well, it's usually ray tracing is usually one of the first homework problems they have in a computer graphics class. So we'd probably just be better off writing our own if we want to get more sophisticated than this. But this got us off the ground and running. Do you think ZMAX would be up to the challenge of arbitrarily putting in a lens at any orientation? It might take some effort, but you probably...
I don't think it would take a whole lot of effort.
Yeah.
But
Okay.
It gives you a scripting language and things. Like,
You can write C programs and interface them.
Okay. Yes.
Is there any reason to believe that the wing shape is better than other asymmetrical shapes, or is that kind of the first thing you tried? Have you tried, and also, I guess related to that, have you looked at all reflective optics as opposed to transmissive?
We haven't looked at reflective objects yet. But the problem with reflective objects is they tend to be rotationally unstable. If you just think about a piece of glass, for example, a mirror, once it starts rotating, there's not going to be any position of stable rotational equilibrium. It'll just keep rotating. So it didn't seem to be the best approach for that. But we would like to look at putting little reflective elements cleverly, maybe on the back surface, to help enhance the amount of either forward thrust or the amount of lift. One thing we learned about the airplane wings is there are all kinds of airplane designs, right? Every airplane, a jet fighter is designed for a much different situation than something to spray fields with pesticide. So there'll probably be different kinds of configurations that would be good depending on what the material is, what kind of forces that are needed, how fast things need to be to react. So it's the very early stages, and we did just try what seemed to be what nature sort of gave us. We have looked at just like rectangular. You might think a simple refractive rectangle would just be stable in sort of the configuration that sort of optimizes the symmetry. But actually, it doesn't. Actually, or even a rectangle will rotate to some position and end up exhibiting lift. So it's really hard to know from the symmetry what is the best. We've looked at triangles. We've looked at trapezoids. And we're trying to come up with some general idea about how the lift may be optimized. But so far, actually, the semicircular cross section looks pretty darn good. Okay. Yes.
I just want to point out, if you do go to an optical design program, some of the advantages would be that it's very easy to define very complex shapes, and they have real sophisticated optimizers to do them.
Okay. If we can do that flying carpet geometry, that would be great. If you think we could program that in, that's one of the challenges now, is how to make that in a way that we can really kind of mold it in a clever way to see how that functions. Yeah.
In your solar cell design, your steering elements aren't free floating, right? They're fixed to the solar sail itself. So it doesn't seem like you need stability to rotation. You can still use a mirror and an optical shutter and get your deflection without any refraction. What the problem is with that, the way you could with a mirror. Well, okay, maybe you want to have things where you can actually like louvers to control the mirrors. Your shutter idea, just having lots of light,
yeah,
and there's no steering, and then open it, and there is steering.
Yeah. So what happens in that case is that the entire structure would then feel more force on one side or the other, so it would rotate. Okay, like the light would be coming at you, so the thing would feel more force on one side or the other. It would go like this, and then there'd be a transverse force because of that change in angle. Okay, but as I said, there's no rotational stability there. So you need to have gyros to pick up that. You need to have reaction gyros to pick up that momentum so that you can kind of stop it in that position. Now, these gyros are massive. They take up energy, so it's not an optimal way of controlling the sail.
And what kind of rotation rates do you get with the forces that you have? When your forces are small, right?
Right. Yeah. So
So can you steer a satellite, reasonably speaking?
The forces, let's see, what do I, for a square, was it for a square kilometer? I think, I don't remember, maybe it was a square meter, maybe it was a square kilometer, you get like millinewton forces. Okay, so if we can get half of that into the lift angle, yeah, that's significant. Even if we can get a fraction of that, that's a significant amount of force. You don't have to react. I mean, it's not like, oh my God, there's a moon, and so. Yeah. That's no moon. That's a, so our hope is that we can at least demonstrate that you can get a significant fraction of the forces that they have in the fraction of the scattering force in order to. The things that you're correcting for example, are variations in the solar flux, for example. It's not constant. There can be various variations of patterns. There can be unknown instabilities in the system. So these are just small perturbations we really have to correct for. So that's the concept. Okay, so maybe we'll move on to the next show. This is an imaging problem, and I'm going to ask you if you know what this is, okay, I'm sure, okay. And if I only gave you this amount here, okay, could you tell me how many point sources are creating the amount of light that you collect, you see from here, okay. Could you get what kind of information could you get from like the this airy disk pattern here if you're only given a very small part of that? Okay. It's very hard to get any information. For example, what if I told you there were two light sources? You just had the classic problem of resolution, right? And these two light sources were very close together, and so it looked like just one point source at infinity, right? But I'm going to tell you, I can look at this, and I can tell you that there's more than one light source. That's some information, okay? And so there are ways of actually getting rid of the stuff that looks like it's coming from a single light source, so that you can start to uncover the information of the distribution of light from this object. And that's the concept here. This is some work I just published in Optics Letters. Okay. So this is based on some of my favorite topics in science. That's the physics of vortices. And vortices span all different physical systems in both coherent systems as well as for incoherent systems. And whenever you tend to look at vorticity or circulation in systems, you always find something rather interesting and marvelous. And so, in some sense, my whole reason for studying the previous talk of optical lift was based on how can we use light in order to, knowing that it has circulation, how can we use it to create this thing called lift? Well, we didn't talk about vorticity in that system. I won't. But now we're going to probably talk more about this picture. What is in the eye of the hurricane? Why do airplanes fly into the eye of the hurricane? Why don't they fly outside here where the winds are buffeting the aircraft at hundreds of miles an hour? Well, one reason is that the plane would be shredded, okay, way out here is, okay. But the other is, I mean, there's something about the system that the temperature, the pressure, the wind speeds here, they characterize the system. When you look in the eye of a vortex, there's something to behold, okay? So we're trying to take advantage of that. So if you don't know what an optical vortex is, let me educate you on that. You've all seen probably in advanced math physics class some wave function that's separable into a radially dependent part. Let's just say this is in 2 dimensions. So this is x and y, and azimuthal component here. And this component here is called the vortex term and the vortex factor. And this m here is what we call the topological charge. So you probably all know laser beams. You probably hope your laser beam has a phase front that's nice and flat. Okay, but in fact, many laser beams have these different higher order Laguerre-Gaussian modes, and so this would be one where the phase varies from 0 to 2 pi around some point. Here it would vary from 0 to 4 pi, 0 to 6 pi, etc. So in these cases, you have circulation of light around this dark core here, and it has vorticity, it has circulation, it has angular momentum. Okay. So I don't really want to get too much into all the beauty of vortices, but I'm going to use them, and we're going to use them in Hankel transforms and in decomposing objects. so we can understand them in terms of vortices. So one classic way of doing this this decomposition is if you have some image, let's say Lena here, and you just rewrite her in terms of radial and azimuthal coordinates, so you end up distorting her quite a bit. But you can integrate. You can find out what these radial components are for each value of m, where m is some integer plus or minus 1, plus or minus 2, 0, etc. Okay? So you just integrate. You integrate around theta. So if you take a position r and you integrate across theta, then you come up with a value with what a of some m is here. So let's say you do it for m is equal to 0, you get one value. You do it for m is equal to 1, you get another value. M is equal to 2, you get another value, etc. So you end up with what we call a topological spectrum of this. And so you see this gets converted to something quite beautiful, actually. Okay, so you get basically a very. You got to admit this mathematically is more beautiful than this, right? Okay. So you see a very large mode at just the plane wave mode, basically, just the place where there's no vorticity, just the m is equal to 0. But then you get modes at m is plus or minus 1, plus or minus 2, and they're symmetric here because it's a real object. But so what we want to do, we want to think about how do we decompose things in terms of this, we call it topological spectrum, and then are there cases where you can actually use it, not just for art, but for something else. Okay? So this is what we want to use them for, and it's based on what we call the optical vortex coronagraph. And that coronagraph is an instrument that was first developed by Bernard Liot to mimic the corona of the sun, but now it's a common instrument that astronomers use to look at, let's say, block out a bright star so they can see features around the star. Okay? So basically you have a telescope, you have a focal plane, you have a recollimating lens here, and you have something here called a leostop, which is just an aperture. Okay? So the light goes through the aperture, if there's any light there, and then you focus the light and produce an image on some detector. Okay? Now, what Bernard Liot did is he put a piece of black material here so that you block the rays that were from a light on axis, but you let light through that came from an off axis source, and he was able to make a decent corona of the sun without having to wait for an eclipse. Okay? What we're doing is we're putting an optical vortex lens here. Now, a vortex lens is a piece of glass that has the spiral structure. That the height here, I don't know if you can see this, I have another picture of it here. The height varies from some base level up to some value where the step here corresponds to one full wave of phase retardation. So since this happens twice, we end up producing a vortex of topological charge 2 here. Okay? So these we call vortex lenses or vortex phase masks or spiral phase elements. There's a variety of names for them. But what happens is something really quite beautiful that is like when you will have one of these aha moments in your careers, I hope, when you do a calculation, then you just put your pencil down and say, wow, something must be wrong here. This is just too beautiful. Okay? What happens if I have a plane wave coming in here, it produces this Besink function, or what do you call them here? Sombrero functions or airy disk function. You have basically a PSF here, okay? And you put a vortex lens here, and if the center of this airy disk here falls right in the center of this vortex lens, then what happens in the plane of this leostop is that all the light is diffracted out into this ring here with the center completely black. So if my leostop with this aperture here basically is just like that, then no light will get through the detector here, and I won't see anything. So my image is black. Okay. So what is this telling me? This is telling me that I've basically taken away a plane wave, basically this on-axis plane wave component of my image. Now it turns out that things that come in at different angles will go through this. If their spots don't fall right on the optical axis, they'll come through this system unaffected. So I have a way of extracting out, eliminating this plane wave component of the light source. So we can do this in a lab. For example, we can just take two optical fibers, put red light in one, green in the other, send it through, and you see the green light here is on the optical axis. This point here would be on the optical axis where the vortex lens would have its center, and the red beam is not. So one of them gets blocked, the green light gets blocked, but the red light is allowed to come through. Okay? What we've done here is we've demonstrated a way of extinguishing. Now what if these two things were very close? Okay? How well can I eliminate this green light so that I still know that there's a red beam there? Okay, this is the whole object of can we resolve two things that are very close together, and how far can we actually push that? Okay, so that's what we want to talk about here. This shows us what we get in the laboratory, for example. We call this a ring of fire. You can kind of tell why. We're interested in finding out, asking ourselves, we have a little bit of light in here. What does that light tell us about the system? If there's light in here and everything else was perfect, it would tell us that our light source was not a point object at infinity or not a plane wave coming in right on the optical axis. It would tell me there's something else in that beam. Okay? So how do we mathematically quantify that? And does it tell us that maybe there's another object there at some unresolvable distance away? And if we can say that, then we have information about a system that's unresolved. Okay? So the thing to realize here is that if I have this, what's called a Besink function here, if I multiply this by just 1, okay, then the Fourier transform of that basically just recovers the image of the aperture of my system, of my telescope. Okay? No surprises there. If instead I multiply this function here by a phase with a vortex of charge 2, then I get this ring of fire here. Okay, I get no light in the center. Okay, so these are some Fourier transform pairs. The size of these two are the same. So the size of this corresponds to the size of the aperture of the system. Okay, so that can be actually quite a large disk of darkness. Okay, so the question again is, what if the light source is slightly off axis, for example, or what if I have an extended source or multiple sources in the field? How do they go through? How do they pollute, basically? How do they send light into this ring of fire, into this dark region here? And can I collect that, detect it, and then say something about the distribution of the original light sources? Okay. So as I suggested a little bit earlier, if you caught it, if the center of this vortex lens, this shows another example of a vortex lens here. If the center of this is right in the center of here, then I get, if they're aligned, then I get this ring of fire, okay, this dark hole. But if they're misaligned, okay, if this singularity here occurs over here, for example, then all the light will go through this system. Okay? So keeping this in mind, we want to know what happens kind of in the in-between stage. What happens with either just slightly misaligned? How can I understand this and use it for saying something about the objects? Okay? So we got to go back to the source, okay, of the object. Okay? If an object is very far away from some telescope with some aperture r, then I can decompose, just as we did for Lena, I can decompose the object in terms of the circular harmonic decomposition, where I have these coefficients in front of the vortex factor b. Okay? And each b depends on the topological charge L of this mode. Okay? Now, the light I collect at the telescope here is very far away, so I can just do a Fourier transform. A Fourier transform in circular coordinates is just a Hankel transform. So it's an Elf order Hankel transform. So I can write it like this. And this Hankel transform is just basically this function b integrated over the Elf order Bessel function here. Okay, so we can, in principle, do that. Okay. All right. So now I'm saying, what if this object is extremely small? Okay, A is very small, or it's very far away, or the radius of my telescope is not a meter telescope. But what if I have a 1 millimeter telescope? Okay, it means that this factor here is going to be extremely small. Okay, and this is really the scaling of the whole problem here, because this scaling occurs in the Bessel function that we have. Remember, we just had to integrate over a Bessel function. So if this factor is small, I can write my Bessel function, alpha order Bessel function, in terms of a series, and now I can truncate higher terms of that series, just keep the lowest order terms. Okay? So what this means is that the electric field at the telescope is now given by, the important thing is some coefficient, which you can calculate, and let's not worry about that. Okay? Okay? It's given by something that depends on the radius to the p's power. P is the magnitude of the topological charge of the Elf mode plus 2n, where n comes from this superposition here. So there's a whole series of modes here that we can construct. And then each of those modes has some topological charge L. So the beautiful thing is that this goes as some radial part and then times some vortex charge. Okay, so we just can add all those up. Or we can just propagate each one of these modes through our system and ask, how do they propagate? Okay? So what we find is that when you propagate to the Leo stop back here, you basically get a solution that is, again, a separable function. One part depends on the azimuth. The other part depends on the radius. Okay? And the azimuthal part is not that interesting. There's some vortex stuff here, but it's some number. The important part is that what is this coefficient, this radial dependent part of the function at the Leo stop here? It's ugly, terrible looking double integral with the two Bessel functions on different orders. Okay, so it turns out that if you spend enough time paging through integral tables, you find that you can actually get someplace with these functions. You can actually solve. There are analytical solutions for these integrals. Okay, so we want to look at just a classic example real quick. What if we just have a delta function here? A delta function will tell us that the lowest order mode that gets to our Leo stop will basically tell us that, well, if the vortex lens that we put in, remember we have this vortex coronagraph that has some charge m. So if the vortex has a charge 0, that is basically no vortex lens at all the light gets through. So it looks like a point source because this distance is is an unresolved distance away. So this looks like a point source. If the vortex has an even topological charge, then no light gets through. So this is our ring of fire. Okay? So the lowest order mode for this system, for this delta function, basically looks like a plane wave coming through the system. And my vortex, as long as I have an even topological charge for the vortex in my vortex coronagraph, I can eliminate that mode. That's the plane wave mode. Okay? That's the thing that I want to eliminate. Now I'm left with everything else. Okay? So let's look at the next higher order mode. The next higher order mode, well, one of those modes is 0, so it doesn't really give me anything. But another mode of the same order gives me something that depends on the radius in the plane of the Leo stop. And there's some phase here. But I can find the intensity. I can just take the modulus square of this now, find out what the intensity is. I can integrate across the entire Leo stop, and I'll get the power. So how much power do I have in that region that ring of fire was dark inside? Now I'm saying some of these modes, if that point is not right on the axis, there'll be some light coming into that system, and it will. I can measure how much power. Okay, so the power is just the integration over all the modes, if you like, through the system. And what I'm most interested in is comparing the power for a vortex of charge 2, for example, for this Leo stop, or for the coronagraph, a vortex of charge. The power. What happens if I put the vortex lens of charge 2 in there, measure the power in that dark area, then take the vortex lens out, measure the power again, this ratio. And this ratio is something very simple. It just gives me this gamma squared amount. This number is small, but it's measurable. Okay? So now, if I measure this fractional power, it's basically telling me that there's some off-axis light source there, that thing is not on axis. Okay? Now I can just do that for any number of point sources now. I can measure the light through that dark ring of fire, the dark region of the ring of fire. I'm not forming an image, I'm just measuring a power. Okay? So I'm making a simple power measurement, basically two power measurements, one with the vortex lens in, one without. I can extract, first I can find the minimum of this distribution because the fractional power is going to be a minimum when the telescope is directed right at the centroid, and also the amount of power I have when it's in that orientation is going to tell me the variance of that distribution. Okay? So that shows this blue curve here that if I'm right on the optical, if the telescope is pointed right at the distribution that I cannot resolve, my telescope would think that it would look like just a single point source, but with this playing this game with the vortex lenses, it gives me some finite amount of power here. This finite amount of power tells me what the variance is of that distribution. Now I found basically that the object is not a point, but it's something that has some radial variance. It has some distribution in space. That's information. Okay? So the next stage that we're doing is we're trying to ask how can we get higher order moments of this distribution? Can we look at rectilinear moments? Can we look at other circular moments of the system in order to start building up more and more information about the system? If you measure enough moments, you can reconstruct the object. Okay, all in something that could be a millimeter-sized telescope. Okay, now that might be extreme because not a lot of light gets through a millimeter aperture. Depends on what you're looking at, but you could go up to slightly larger scale if necessary. And I think that's it. I think that's the concept there. So you have to do special thing, make sure that you follow some good procedures for your images to do background subtraction and stuff. But eventually we hope that we can show that for small apertures and long focal length lenses, there's lots of advantages. For example, such systems will be lightweight, inexpensive, low aberrations, not only through the optics, but through the atmosphere. A very small aperture will undergo very little atmospheric aberration compared to something that's extremely large. We get high Strehl ratios in such systems. You could use this then for targeting and tracking. We like to use it both for looking at distance objects very far away, but also for things under a microscope like nanoparticles, fluorescent probes, and things like this. And so there's a list of things to do, but the future now is to try to find ways of showing not just one moment, but now a whole family of moments, and we're on our way to doing that. So thank you for your time. This work was done by graduate student Joshua Hahn, Mark Dennis at the University of Bristol, and other collaborators here that help work on the chronograph stuff. Some of them now are at JPL and gone on to other places. Okay, so thanks for your time. It depends on what kind of noise you have. We threw in some noise here just sort of as a comparison, and we're trying to compare a little bit like apples and oranges here. It's not really quite a fair comparison, but if we just have additive noise, you can see that you can actually, if you have some distribution of information here, that this stuff is more, it changes more over a small scale than you would with just a standard the telescope where it was unresolved. So it would be hard to find the centroid here. It would be hard to know if there are multiple objects here. So, but if you want to get down to a quantum noise level, that's another question. We haven't worried about that yet. But I think as long as the problem is that I guess you might ask how much light are you throwing away in these higher modes, and so you end up throwing a lot of light away. So these are the contrast. I guess you can think of the contrast of these systems is the plane wave mode you reject on the order of could be like 10 to the minus 6 or so. Okay, so you're throwing away a lot of that, and you're probably throwing a good fraction of that away from these other modes as well. So it's not terribly efficient. So you would want to look at bright light sources or be able to integrate for a long enough time to accumulate enough signal on these. But yeah, we're just starting to do this, so detailed noise analysis, we don't know. Yeah. Maybe the back of the room first, student.
So these vortex phase masks, at least last time I looked at them, they were sort of discrete stair-step kind of photography on glass things. So is that stair-step shape as opposed to a continuous smooth shape affect the resolution you can achieve with these devices?
You would think so, but actually it turns out they don't. As long as you have an even number of steps, if you do the circular harmonic decomposition of these things, then they end up giving you basically, you still get your nice ring of fire that can be completely black inside.
So maybe with 2 steps, it would work? The number of steps.
You can do, well, not 2. We could use 4. You could have 0 pi, 0 pi, for example. That would give you some sense. But the problem there is you end up getting radial structures in that system. But there is something called the 4-quadrant phase mask that achieves chronographic performance. And astronomers have been using that for years. So it's possible. We'd like to try to create one that's smooth, or actually the folks at JPL are using some liquid crystal-based ones now that are quite well controlled and are more, they use some way the diffraction grading approach, which gets rid of a lot of those problems with the steps. Okay.
And if you don't consider noise or construction errors, what limits the resolution of this system?
Well, I wouldn't call it resolution, but I guess what you know, how many moments can you actually extract out of this would probably be the thing that would limit it. So you start getting down, if you go, so this depended on this factor gamma squared. When you probably go to a vortex of charge 4, for example, you probably can expect it to go as gamma to the 4th power. So this thing starts going down very, very deep. So you're really going to run into a noise floor someplace because you may not be able to measure the that.
There's no aperture limit on resolution, except as it applies to the
Right. Yeah. I don't see. The only thing is because you only measure a power, so it's just a matter is there enough power there to measure, and we're assuming here very small apertures, right? So if you might, you might have, well, I don't know. Yeah, we haven't analyzed this for a very large aperture, but that's not a problem. That people can resolve things with large aperture, so that's not our question here. Okay.
Could you comment on what you'll replace the vortex lens by if you're trying to extract rectilinear moments, especially higher ones?
So we would put a basically we want to know how much light goes through the ring of fire, okay, into that dark region. So we put a rectilinear feature there. Actually, Joshua on students, he's done a master's thesis examining this already. And basically, the rectilinear features will then discriminate between things that are scattered off this way and things that are scattered off this way in that dark region. So that's a way of getting rectilinear information out of it.
But still using the same vortex.
Yeah, same vortex. Yeah.
That's perfect.
Yeah, I wonder, have you thought about whether this would make a good technique for diagnosing laser beam waveforms? Does it have advantages over a sort of m-squared type measurement?
Mm-hmm. So yeah, so we would. Well, I mean, this is one of our problems. Is we want to make plane waves. How do you make a plane wave? To within.
The laser looks like coming from a point.
Right. Yeah. So.
So it seems like there might be a way to characterize in terms of what extent it looks like.
So I guess yeah. So yeah, I guess so. So no, you have two things in the laser. You have the wavefront, but you also have the Gaussian envelope. So if we stick a Gaussian envelope in here, how will these different things come out? And can we measure? So you asked me, can we measure m squared in another way by just doing a simple measurement of making these two power measurements, for example?
M-squared in another way, but, for example, one issue with M-squared is that even beams that don't look that great can measure a pretty good M-squared.
Mm-hmm.
I think that's saying something about the fact that the phase odds may be pretty good even if the spatial distribution of the light is a little not uniform.
Mm-hmm.
So it occurs to me maybe somehow this would be useful.
That sounds good. We should look into it. Thanks. If you have a student you'd like to work on it, let me know. Josh Ron's graduating so in a couple of weeks. So yeah, it's yeah.
The use of vortices for super resolution is supposed to be for 20 years ago, and there's always been this problem with the signal noise and prior intention. So here you're assuming you can isolate different point sources. How many can you resolve? I think you mentioned how many point sources.
Yeah. So again, we're not really trying to resolve anything, right? We're just trying to say what is the variance of that distribution? What are the moments of that distribution? And can we get enough? Let's say you may not be interested in the object per se, but you just want to know. Let's say if you're some agency that wants to know if you have something that's long this way and short this way, you know, what's the aspect ratio? Can you start getting some information about that without actually reading, you know, USSR on this side or something like that, right? You know, so yeah, we're not going to try to push the concept of resolution here, but just start getting some information about the system that would be useful. For example, I suppose if you had two nanoparticles close together, what you'd like to know is it just one fluorescing, or do you actually have two of them fluorescing? And if so, then you may be able to pick up what that distance between them is.
But there are precise measures to quantify that. It's not clear to me what are the equation assumptions here. Are they just particles, one that
Yeah, and a continuous distribution. I mean, we're looking at you know, you can do this all on the computer, right? So you can end up putting any distribution you want in here. So the question is, you know, what's the best system to apply it to? Okay, so for example, space debris. There's lots of small things in there you can't resolve. But you like to know, you know, is it, you know, does it have some shape to it? Because you like to monitor that and you keep track of all these things. You know, can you find problems where you can apply this? And so, we're suspecting that in the astronomy regime, if the atmospheric stability is not a killer, then that's going to be one regime. In the microscopic regime, there's probably a whole other set of possible applications where you're probably not beating against aberration so much. But this is just the beginning stage. Okay, here's a tool. Now let's see if anyone wants to actually make this vortex chronograph, and I'll keep the thing aligned to actually use the tool.
That's Professor.